Hello there. Welcome to Astraveo's continuing education series, where for our podcast listeners we talk about mathematics, the physical sciences, of course the natural world, and our personal favourites, astronomy. Now, you know Joseph and I are all up in and about astronomy. We get super excited about that stuff. So let's get going. Hello, welcome back to Astraveo's Maths is Just a Game series as part of our education series that we have been running. We've been off air for a little while, partly because both Joseph and I have been doing some astrophysical research, and so of course we have to get our own work done as well. But I do tutor some kids in the community, as you know, I mentioned last time, and they've been bringing up some really interesting questions, and they've been asking me, hey, why aren't you doing your Maths is Just a Game series anymore? So I decided to jump back into it because, you know what, both Joseph and I are we're sort of members of the Geekalati. We both are we're both pretty big geeks ourselves. We love science and astronomy and mathematics, and so this is sort of right up our alley anyway. So for today's episode, I'm going to put this equation on the board, on the screen here. Solve t to the power 4 minus 4 to the power t equals 17. Now, at first glance, this looks really tough, and you're thinking, oh my gosh, this is a college level question that he's asking. It's actually not that bad, and in fact, if you remember some of the law of indices parameters that we discussed in one of the earlier Astraveo videos in the education series, you can actually do some playing around. Now, as soon as you see t to the 4, there's some numbers that jump into my head there. Automatically, I'm thinking, well, that's sort of t squared squared. So I'm sort of already starting to feel good. I'm starting to recognize there's something I can do here. All right, so let's get into it. Let's have some fun. Okay, I'm seeing if I can change screens here because I'm now doing it on a laptop instead of on the board like I was doing it before. Okay, so just to reiterate, here is our Maths is Just a Game question for this week. What is the solution to the equation t to the power 4 minus 4 to the power t equals 17? Again, at first glance, you may be thinking, oh my gosh, this is really difficult. But it actually isn't. So I'm going to put the equation back up. And what you can do is, oh, I thought I had a fancy laser pointer. Let me see if I can get a nice laser pointer. I thought I did have one. Yeah. So what we can do here is we can turn this t to the power 4 into a t to the power 2 times 2. It's squared. So essentially it's t squared times t squared. And then you can do the same with the 4. You can deconvolve it into 2 to the power 2. So that's all raised to the power t. So now we've actually deconvolved the first equation, and we're starting to now see some interesting patterns come out. Well, don't forget, you recall, if you have some number to the power x times y, here I've rewritten it as x to the power a to the power x to the power y. Due to the law of indices, you can actually swap these out. A to the x to the y can become a to the y to the x. So what we're going to do is we're going to actually use that here in this expression. We're going to swap the 2 and the t's. So instead of it being 2 to the power 2 to the t, we're going to make it 2 to the t squared. And that's really useful now because not only as before we had 2 squared squared, I'm going to write that as t squared squared minus 2 to the t squared equals 17. So we've been able to rewrite that equation to make it look a little bit more simple compared to what it was. This is really useful for us because it's easy to deal with things that are squared. It's very difficult to deal with parameters that are to the power t, because we have no knowledge of what t is, and so we don't know how to deconvolve that number very well. So what else can we do with that number? So we can say, I'll tell you what, let's let t squared equal x, and we'll call that equation 1. And then we'll say, well, let's let t to the power 2 to the power t equal y, and we'll call that equation 2. Now, perhaps at first glance you're thinking, well, hasn't he just complicated things? It's actually, I think it's quite the opposite. I've actually simplified it because it's easy to get confused with t's and 2's and 2's and t's. That's not that easy to say, by the way, but t's and 2's and 2's and t's can become confusing. If we now replace t squared with x and 2 to the power t with y, we actually have a much simpler equation. We can now derive or constrain this equation to be x squared minus y squared equals 17, just by substituting in t squared equals x and t2 to the power t equals y. So now we're starting to look at an equation that's looking a little bit more simple. Okay, well, what else can we do? Can we play around with this? Well, from our simple algebra, we know that we can expand out this expression to be a plus b times a minus b. And if you were to work backwards, you would get a times a, which is a squared, minus b squared, there's the minus b squared, plus ab minus ab. And those two cancel, so you're left with a squared minus b squared. Now we have a sort of a squared minus b squared type equation here. It's x squared minus y squared. As it happens, we've changed our parameters, changed the algebra a little bit. So now we can perhaps turn something like this into an expanded form like this. So what we're going to do is we're now going to rewrite x to the power 2 minus y to the power 2 as x plus y times x minus y, and we can rewrite 17 as just 1 times the number 17. Well, that's really interesting, but we can also write it as x plus y times x minus y as equal to 17 times the number 1. Both of these statements are correct. 1 times 17 is 17 and 17 times 1 is 17. So the right hand side of the equation actually looks exactly the same. Now, why can we use the equation in this form? Well, it turns out it's really useful. So I've just rewritten it on the same line here. X plus y times x minus y can be 1 times 17, or that same expression can be 17 times 1. However, we know that if we can allow x plus y to equal 1, or we can allow x plus y to equal 17. And conversely, we can also allow x minus y to equal this part of the equation, 17, or we can allow it to equal 1. And we're allowed to do that because this dot is a multiplier. So this dot represents this times, and this dot represents this times. So which one should we take? Well, we know that x plus y is very much greater, or at least greater than x plus y, x minus y, I apologise, because just you could throw a couple of numbers in here empirically. 2 plus 3 is greater than 2 minus 3. We know that to be true. So what that allows us to do is you can reject the 1 times 17 equation, because the first number, the first expression, has to be big, and 1 is not bigger than 17. So we're going to go ahead and reject that first one, and we're going to accept that x plus y times x minus y is in fact 17 times 1. Okay. Now, with that knowledge in hand, we can actually do some nice little mathematics. We can say this number, this parameter here, equals 17, and this second parameter equals 1. So we end up with the equations of x plus y equals 17, and we'll call that equation 3, and x minus y equals to 1, and we'll call that equation 4. Now that's really good because we have two unknowns, x and y, and we have two equations. It's a fundamental of mathematics that you need at least the same number of equations as your unknowns, although that system of equations cannot be solved. So this is very nice that we have two expressions and two unknowns. This set of equations can now be solved. And of course, one of the easiest ways we can do this is just add the two equations together, and plus y minus y will cancel out. So let's go ahead and do that. Let's add together those two equations. X plus y plus x minus y is 17 plus 1. Well, that turns out to be really nice. When we expand out the brackets, we can cancel the plus y and the minus y to just leave us with x plus x equals 17 plus 1, which is 18. So 2x equals 18, divide by 2, x equals 9. We have solved one of the numbers that we need. So that's really useful. So let's recall our equation 3, where we know that a very simple algebraic expression that x plus y equals 17. Well, we just showed that x equals 9. So now we could do some very simple mathematics to show that if we subtract 9 from both sides, y equals 8. So we now have the two parameters that we needed, x equal to be 9, y equal to be 8. Now, how does that help us? Well, let's go all the way back to the beginning and recall equation 1 and 2, that we have t squared equals x and 2 to the power t equals y. Well, we now know x and y, we actually know their values, so we can substitute in that t squared is 9, because x equals 9, and 2 to the power t is 8, because we proved that y equals 8. So this is really, very nice. So moving on, t squared equals 9. Now we can sort of deconvolve 9, because it's a perfect square. We can have t squared equals 3 squared. 3 times 3 is 9, as we know. Well, if we take the square root of both sides, The square root with the square of t cancels, and the square root with the square of 3 cancels, and so you're left with t equals 3. You've solved for t. Now, does that work for the other equation, 2 to the t equals 8? Well, yes, because what we can do is we can say 2 to the t is actually 2 to the power 3. We've deconvolved 8 into 2 cubed. 2 times 2 is 4, times 2 is 8. So this equation is copacetic, it works very nicely. Now recall that if you have some number equal to a power, equal to the same number to another power, those two powers have to equal each other. So here we can say that t has to equal 3 because we have the number 2 as the base power, as the base number there. So 2 to the t equals 2 to the 3 implies that t equals 3. Now that's really very nice because it coincides with the first equation. There's only one set of t values that we can have if you have a non-degenerate solution. So now we've proved that t equals 3 for both sets of equations. Well, let's perhaps go ahead and do a check and see if those numbers work with our equations that we started with, or the equation that we started with. So we started with t to the power 4, subtracted from 4 to the power t equals 17. So let's substitute in t equals 3 and see what we get. Well, that gives us that would give us 3 to the power 4, because t is 3, minus 4 to the power t, again t is 3. Well, what that equals, we can deconvolve 3 to the power 4 as 3 squared times 3 squared, and 4 to the power 3 we can subtract off 4 times 4 squared. That would give us a cube. Well, 3 squared is 9, so 9 times 9 is the first set of expressions. 4 squared is 16, so we can have 4 times 16, which gives us 81 minus 64, which does indeed give us 17. QED, quod erat demonstradum, we have shown that when t equals 3, t to the power 4 minus 4 to the power t equals 17. So mathematics is just a game. We started off with really what was a sort of complex equation. Wasn't that easy to solve, certainly couldn't do it in our heads easily. And you're thinking, oh, that's a university level entrance exam. I couldn't answer that. But by remembering your simple mathematics and the law of indices, and we have discussed the laws of indices in one of our previous educational series videos, we're able to show that with just a little bit of playing around, a little bit of mental arithmetic and juggling the numbers, we're really able to find the solution quite easily, and we have been able to do that. So please don't get worried when you see complicated mathematical expressions. There's often quite a simple solution if you just remember the basic fundamentals of maths. And maths, just remember, maths is just a game. Always tell my children that, it's just a bit of fun. A lot of the time you're just juggling numbers or square roots or squares or looking for geometry or relationships between various things. If you know your squares, your cubes, your quartic numbers, and you remember some of your algebraic expressions, you can do some massaging of the numbers and some rearranging of the data really quite nicely. Alright, thanks for joining us. I hope you enjoyed the episode.